Hello and welcome to our next video for Stat 212. In this video we're going to talk about hazard ratios, which is a lot like relative risk, or sometimes they're called risk ratios. The only difference here is that we're kind of adding a time element to comparing the risk between two different treatment factors, two different situations. So again, we're really just doing relative risk, with the added element of looking at risk over a particular period of time and risk comparison. So whenever you're looking at hazard ratios, you might commonly see these Kaplan-Meier curves, or sometimes they're called just a Kaplan-Meier plot. And this is kind of the risk of our various factors over a period of time. So for example, here we're looking at a hazard ratio. So the hazard in this case would be death. So how many people die over a certain period of time, and this is in this case scaled in terms of percent, so percent survival. So the larger the drop, the more folks have passed away in this particular group. And we're comparing the survival here of two different groups here. So obviously the group represented in green has a much higher hazard than this group over here in blue. And so what we can do with this time element is that we can compare this hazard ratio at different periods of time. So obviously in the first day or two here, we have a very similar drop-off, but then from that point onward, we're seeing that gap kind of rise, and we're seeing each group kind of plateau at their own time. So in this case, maybe the time element isn't super important because the rates seem to be pretty similar at any given point that we might look at. However, there might be some cases where our hazard ratio, or I should say our Kaplan-Meier curve, shows changes in which group seems to be more hazardous at different periods of time. And so calculating hazard ratios for any given period of time can be helpful for more targeted analysis and comparison. So a hazard ratio is calculated by finding kind of this hazard, number of new cases, number of new incidents. So when I call this cases, by the way, something to kind of point out here is kind of outcomes of usually concern when we're doing a hazard ratio. So like, for example, death. So like each new death or each new illness or something like that is going to be a case that we might be talking about. Over the total number that we started with over the beginning of a period of time. All right, so number of new cases divided by number from the beginning of that period. And this is going to be divided by number of new cases for the other group. So oftentimes it's like a control group or some kind of other treatment factor that we're comparing it against. Number of new cases divided by the total number of cases from the beginning of that time period. So therefore, we can kind of choose the time period of interest, and that ratio, that hazard ratio, is going to be different depending on that time period that we're focusing on. So we're just going to get straight into it, and we're going to do some calculations with hazard ratios, where here our data is provided by number of kind of remaining uninfected plants at different time points. And we can use this information to kind of discern how many plants have been infected at different time points. So the context here is that we're looking at plant damage due to a bug known as a thrip. This is a plant-eating bug that's going to rot the plant. So we're comparing two different kind of treatments or preventatives for this happening. One is going to be a rove beetle predator being introduced to these 100 plants up here. The other is going to be a pesticide treatment used on these other 100 plants over here. So 200 plants are randomly assigned to each treatment, and then we're just going to follow over time to see how many plants remain uninfected at different time points. So again, we can kind of discern from this information that if 89 plants are uninfected at day 14, that means that 11 plants are newly infected at day 14. And etc. So if 68 are uninfected by day 28, then 32 are infected by day 28, etc. So what is the hazard ratio for the first 14 days? So that's going to be the number of new cases, in this case, new infections, newly kind of infected plants by this rot, by the thrips. So number of new cases for the beetle treatment. So I'm going to do beetle over pesticide. And I'm doing this because it seems that this is the new treatment that we're comparing. So this is kind of our treatment of interest, and we're comparing it against kind of this pesticide, which is kind of our baseline, our comparison of what we would normally do. So we're going to have 11 new cases out of 100 that we started with in this 14-day period. And for the pesticide group, it's going to be 6 new cases out of the 100 that we started with in that group. So then if we complete this calculation, the hundreds are going to cancel out because we're dividing by 100 in both the numerator and denominator. So it's really just going to be 11 over 6, and that's going to be 1.833. But what about a hazard ratio for a different period of time? So maybe not starting from the beginning, but starting somewhere in the middle to another time point. So we can do the hazard ratio from days 14 to 28 to see if there's a difference in hazard and the infection rate between these two groups. So here we're going to look at number of new cases within that 14-day period divided by where we started with. So again, for the beetle group over pesticide in the denominator, we have 68 left up here where we started with 89. So number of new cases is going to be 89 minus 68 over the 89 that we started with. And the denominator is going to be this 94 minus 68 divided by the 94 that we started with. So again, we're finding that difference, the number of newly infected plants in this period of time divided by where we started. And so this numerator here is going to be 21 over 89. So that's the proportion of plants in this time period that were newly infected. Whereas the denominator is going to be 26 over 94. And then we can calculate that out. So in the numerator, we're going to have 0.2359 ... And the denominator, we're going to have 26 divided by 94. The denominator is going to be about 0.2766 ... So let me just kind of write these out. 2, 3, and I guess I'll round it to 60, and then down here I'm going to round it to 0.2766. And so if I divide these out, I'm going to get about 0.853, 8531, like this. All right, so my hazard ratio here is going to be 0.8531. Notice now that this one is below 1, meaning that the hazard for the beetle group is actually slightly lower than that of the pesticide group if we're looking at the day 14 to 28 period. Whereas for the first 14 days, the risks for the beetle group seemed to be higher. There was a higher hazard for infection in that period of time. Now, again, we mentioned that this is essentially just relative risk. We're just applying it to particular time periods. So if you wanted to calculate relative risk, the assumption behind that measure here is that this is for the entire length of the study. So if we're using the term relative risk, we typically mean from start to finish, whereas a hazard ratio would be a very particular time point that we might be wanting to know more about. So the relative risk measure here is going to be, again, the beetle group over the pesticide group, just to kind of identify which group is going where again. And it's going to be this number of new cases is going to be 100 minus 64 over 100 divided by this 100 minus 44 over 100. And just kind of a notation thing that's in parentheses, that's being all divided by 100 in each case. And so if we calculate this out, we're going to get 36 over 100 over 56 divided by 100. And that's going to give us, that would just be 36 over 56. And this number comes out to 0.6429, I think. 642, yeah, we'll go 0.6429. So that means that the risk for infection for the beetle group is 0.64 times that of the risk for the pesticide group over the entire length of the study over these entire 56 days. So just kind of a recap here, what information did we glean by looking at the hazard ratios rather than simply looking at relative risk. So the information we're gleaning is that the pesticide group might be a little bit more effective in the short term, whereas the beetle treatment might seem to be more effective over the long term. So we noticed that for the first 14 days, the pesticide group had a much better survival rate here. So in this case, and I say might, by the way, because if we remember this is only sample data, these are estimates of what's truly going on if we had infinite number of plants in both groups. So we're kind of saying that our estimate here is that the pesticide group might be doing better for the first 14 or so days. So I'm going to say might be better. In the short term, but the beetle treatment might be better in the long term. All right, and we'll stop there.